Similarly, if the point considered A is very far away, that means distance of the point A in the electric field is far away from the parent charge which is producing the electric field. Parent charge is nothing but charge. It's not a new term. It's nothing but the charge which is producing the electric field itself is called as parent charge. And the charge which is used for testing the electric field is simply called as test charge. Whether electric field is present or not, we are using some charge like a piece of paper. Even it need not be a charge also, any body also can be used like a piece of paper, whether electric field is present or not. So that is simply called as a test charge or a test body. So now when the unit positive charge is considered at a faraway point from the charge which is producing the electric field, then definitely from Coulomb's inverse square law, as distance is more, less force it experiences. So then the field is less, field is said to be weak. So thus, if the force acting on unit positive charge is more, definitely at that point field is more stronger, strength of the electric field is more, and the field experience or field acting on the unit positive charge is less. Definitely at that point, electric field is less stronger, strength of the electric field is less. Thus, the strength of the electric field can be known completely if the force acting on unit positive charge is known. If it is more, force on unit positive charge more, strength of the electric field is more. Force on unit positive charge less, strength of the electric field is less. Due to this reason, it has been defined. Strength of the electric field is simply defined as the force acting on unit positive charge. That's the simple definition of the strength of the electric field. So definition of the strength of the electric field is very simple. It is simply defined as what? The force acting on a unit positive charge placed at a point. That force itself is called as the strength of the electric field. That's the simple definition of the strength of the electric field. So strength of the electric field or intensity of the electric field is nothing but it is the force. So again, I'm writing the definition, you see, very quickly. So compulsorily note down the definition. Definitions you must not take lightly because they are the ones which are helpful in each and every situation. However complicated a problem is, when you're solving a problem, definitions and the fundamental laws or at least the laws of that particular lesson only are the real, they provide the real help. It is a force acting on a unit positive charge placed at a point in an electric field. So this force acting on unit positive charge itself is called as what? Electric field. So force F is acting on the unit positive charge. So really that is placed here in the diagram. So this itself is what now? Electric field. So electric field is defined as a force. What force? Force acting on unit positive charge. But every force is a vector. So bar should be placed. So bar should be placed here. And what is the direction of the electric field? Because it's defined as a force on unit positive charge. Whatever direction force on the unit positive charge acts, that itself is the direction of the electric field. So clearly it's a vector quantity. So the diagram actually I'm shifting a little down because there is no place here for writing anything. I'll just shift the diagram a little bit down. So it is a vector quantity because every force is a vector. Electric field strength E bar is also defined as a force only. So electric field strength is also a vector quantity based on its definition. It's a vector quantity whose direction is same as the force. Which force? The force acting on the unit positive charge. Now just see here. So always, so in order to get the strength of the electric field at the point A, by definition we are putting a unit positive charge and we are measuring the force on the unit positive charge. That force itself gives the electric field strength E bar. But always unit positive charge may not be available. So imagine that instead of unit positive charge at the point A, we are putting some other positive charge, say Q0 units of positive charge. Then the force experienced by the Q0 units of positive charge will be different compared to the unit positive charge. The reason is, even if one charge, this force always, we are considering force on a charge placed at point A due to the charge Q. Always force is present between two charges. So that force from Coulomb's inverse square law is directly proportional to the product of the two charges. So even if one charge is increased, automatically force will increase. So instead of one unit, if more charge is placed, more force is experienced by the the charge that is placed here. So definitely the force on q naught units of charge will be different. So let that force acting on q naught units of positive charge be again called as, for convenience, again F bar only. So this is the force acting on now q naught units of positive charge. Divide the two. What we get is force divided by charge gives force per unit charge. So this is because always distance, for example, distance by time gives distance per unit time. Work by time gives work per unit time. Like that, force by area gives force per unit area. Force by length gives force per unit length. Always in general in mathematics, numerator by denominator gives numerator per unit denominator. This is always a general rule in mathematics. So force acting on a charge q naught, that force divided by charge q naught units gives force acting on 1 unit charge. Force by charge gives force per unit charge only. But what is the force acting per unit charge or force per unit charge? That is nothing but the electric field intensity itself by definition. So force divided by charge is giving exactly what? Force acting per unit charge only. Force acting by charge gives force acting per unit charge. But what is the force acting per unit charge? Electric field intensity only by definition. So this is taken as the defining equation for the strength of the electric field. So calling this as a very important result 1. This is very important. So this is the defining equation for the strength of the electric field vector. So why this is called as defining equation? The reason for this is a direct consequence of the definition. Force per unit charge is the strength of the electric field. When we are dividing force with charge q naught, we are simply getting force per unit charge. So this is obtained from the definition. That's why it's called defining equation. And another way why it's called as defining equation is we're getting this equation from the definition, or from the definition, from this equation also we can get the definition. This is the force acting on charge q naught. So when we are dividing these two, what we are getting? Force per unit charge. So electric field vector, if it is given to be equal to force divided by charge, force by charge is nothing but force per unit charge, which is nothing but definition of electric field vector itself. So from this equation also we are getting the definition. That's why it's called as defining equation for electric field vector. So the important thing here is how, when this equation is applicable. So if in this situation, if F is the force on charge q, that is charge q naught, then E is equal to F by q naught. So if F is the force on charge q naught, then E is equal to F by q naught. Actually there is no place to write then here, so but this is sufficient. So just like a sentence it can be written. So from this we are getting the equation. So if F is the force on charge q naught, then in such a situation the electric field vector is simply given by F by q naught. So and another use of this particular, once we got the equation for the strength of the electric field. So till now we had only definition for strength of the electric. From the definition we got the equation. In most of the situations it is like that only. For example, another example is in surface tension you have learned. Surface tension is defined as force per unit length. That's the definition of surface tension. From that definition we got the equation for surface tension. Surface tension T is equal to F by L. That's another situation. Almost in every situation pressure is defined as force per unit area. And from the definition we get pressure is equal to force divided by area. So always from the definition we get a simple formula. Applying that formula in another law, we'll get a small derivation. From the derivation we can get another new result. So this is a regular procedure in science and technology always. So from this equation, once we got the equation for the strength of the electric field, easily we can get the units also for the strength of the electric field. Now to get the units, easily we'll go to the next page. Actually page is over, so we'll go to the next page. So next page, so this is the next page. So we got the equation for electric field. From that we can get the units of electric field, that is units of electric field vector or electric field intensity, or the SI units. Always important thing is in electricity compulsorily only SI units are used. Only SI units are used. So no other system of units is actually followed in electricity, because only in SI system only all the different quantities units are exactly properly defined. That's why only SI units are followed in electricity. In mechanics and heat, we have seen previously that SI units can be used. SI or MKS units are used. Next, CGS units, sometimes FPS units are also used. But electricity and magnetism. Magnetism is also something related to electricity. Both these parts or branches of physics, only SI units are actually followed. So now what are the SI units of electric field vector? So consider the equation for electric field vector. So E bar is what? Force F bar by Q naught. Whenever we know the equation for any quantity, usually with the help of that equation, units of that quantity can be obtained. Units of that quantity, say E bar, can be obtained. So unit of force in a system is what? Newton. So unit of charge is Coulomb. So force by charge gives electric field vector, means unit of force by unit of charge will give units of electric field vector. So unit of force is Newton, unit of charge is Coulomb. So newtons per Coulomb. So this is the SI unit of the strength of the electric field, or simply the electric field vector. Now it can be proved that Newton per Coulomb is also equal to volt per meter. Now, why it is equal to the volt per meter? The reason for this, volt is actually the unit of voltage. It's also called as potential difference. Now, there is a proper relation between potential difference and the electric field intensity. With the help of that relation, this unit can be obtained for electric field. So, both are one and the same. Newton per Coulomb can be proved to be equal to volt per meter, but that comes in another topic. So, now it's not required. So, now just because this is a very important unit, not just Newton per Coulomb, even volt per meter also is a very important unit. So practically many situations volt per meter is used, but in certain situations Newton per Coulomb is used. So this is the main basic form of the SI unit of electric field vector. So whatever things we are seeing here are simple, nowhere any complication is there. Now one very important thing here is, just observe the previous page again. So we'll come back to this page. Now at the point A, we are putting a positive unit charge. So it experiences a repulsive force. That force itself is electric field. So in whatever direction a unit positive charge experiences force, that direction itself is the direction of the electric field vector. But instead of unit positive charge, if you are putting some other positive charge, that also experiences a repulsive force. So that force also will be directed away from the charge q. So unit positive charge is pushed away by the charge q. That means the force experienced by the unit positive charge is away from the charge q, which is producing the field here. Not just unit positive charge, even if some other positive charge is placed, that also will be repelled. So that also is pushed away. That means in the same direction as the electric field. So whatever is the direction of the electric field vector, that is, in simple words, the direction of the electric field vector itself is called as the direction of the electric field. So electric field, a certain direction is assigned to electric field. What is that direction of electric field? Means whatever is the direction of the electric field vector or electric field intensity, that itself is taken as the direction of the electric field. So what is the direction? Means the direction in which a positive charge placed at that point experiences a force. That direction itself is the direction of the electric field vector E bar, or simply the direction of the electric field. So always, as a general rule, it can be said that any positive charge placed at a point experiences a force only in the direction of the electric field. Supposing a negative charge is placed here, then what happens? So a negative charge, positive charge is getting repelled by the charge, parent charge, which is producing the electric field. But a negative charge placed here, it will be getting attracted. That means a negative charge in electric field experiences a force in the opposite direction of electric field. That is very important. So a positive charge always experiences a force in the direction of the electric field, and a negative charge experiences a force in the opposite direction of electric field. These are very important things related to electric field. They are very simple, directly obtained from the diagram. So these are two very important results. So whatever things we are seeing here are simple, nowhere any complication is there. So we'll come back again to the units. So here a small note point. So this also, you just see here we are completing the running notes at the same time. So without waiting till all the topics are completed of this particular page. So this is much more easier. So a positive charge in an electric field. In an electric field experiences force in the direction of electric field. So electric field direction means same as the direction of electric field vector. Similarly, a negative charge experiences force in opposite direction. So I'm drawing a line here to end the topic, which was the definition of the electric field intensity. So actually, it's very congested, difficult to draw the line here. But still, if the line is drawn, means it will be more clear that the topic is different. The topic is completed actually, and this next topic is different. So next topic, electric field intensity due to an isolated point charge Q. Now this is again a very important topic. So carrying about 3 marks to 2 marks. Now based on the definition, electric field intensity due to an isolated positive charge Q can be obtained. Now the diagram for this is same as the diagram of the previous topic. So we'll just go to the diagram of the previous topic. I'll just copy that diagram here, copy and paste that diagram here. Just here, same diagram as it is, exactly same diagram. This one Q0 is not required here. So the same diagram I'm just copying in the present topic page. So here, the same diagram I have copied here. The only thing is, at the point A, the charge Q0 is not required, only unit positive charge is sufficient here. Now consider an isolated point charge. So this is an isolated point charge. Actually, though the charge Q, it's isolated only. Isolated means it's a single charge without any other charges nearby. That's called isolated charge. And here the important thing here, it's isolated point charge is mentioned. So here a point charge only must be considered, but point charge means it will not be visible. So for that reason, this charge actually in the diagram is shown as a big charge, so that it will be very clear that some charge body is present here. So it's really, strictly speaking, it should be a point charge, but for the sake of clarity, it's not shown as a point charge. Then to find the intensity of electric field at the point A, which is at distance r from the point charge Q or isolated point charge Q, a unit positive charge is placed at the point A. Now this is also, unit positive charge also should be taken as a point charge. Point charge means of zero size, point sized. Again, it will not be visible if a point charge is placed here. So it's shown as a small spot. It's shown as a small spot, just as small as possible. Conveniently, it should be drawn. So like a small spot. So at the point A, the small unit positive charge is placed here. Then by definition, whatever force the unit positive charge experiences, that itself is called as the strength of the electric field. So it's a very simple situation. At the point A, whatever force a unit positive charge experiences at this placed at this point A, that itself is the strength of the, that force itself is the strength of the electric field by definition. So by definition, so very simple. So here little introduction should be given, 2-3 lines. We'll just see that while writing, after completing the derivation. So it's a derivation, it's just 2-step derivation, or not even 2 steps, 1 step or 1.5 steps derivation. So the force acting on this itself is the strength of the electric field. So by definition of what? By definition of the strength of the electric field. The strength of the electric field itself is nothing, it's nothing but the force acting on the unit positive charge. Force on unit positive charge. Forced on plus 1 charge I have written. So it's not that difficult to, so as clear as possible I'll try to put it. Force on, so on I'll put in brackets on. This phrase sentence I'm putting in brackets. Force on unit positive charge. That itself is by definition. So just see here, one very important thing here is force is a vector, bar is shown in the diagram. Even electric field is also vector, bar is shown. This arrow here represents the force. Always a vector is represented by a directed line segment, which is nothing but an arrow. This we have seen in, that is mechanics we have seen. This is a regular representation of any vector quantity. But the problem is whenever equations are written, the vector nature bar is actually ignored. The reason is if a bar is used here, supposing we want to use Coulomb's inverse square law, vector form of Coulomb's inverse square law should be used. So directly Coulomb's inverse square law force between two charges is 1 by 4 pi epsilon naught q1 q2 by r square. That's only gives the magnitude. To indicate the direction, a unit vector also should be indicated. Once unit vector comes into the equations, that equation is called as a vector equation. Vector equations are always complicated to write also. To write, and also they are very accurate, but to write that it takes a lot of time, lot of thinking also. So it will not be accurate if it's written just like that. So lot of care has to be taken. That's why vector equations are avoided in derivations, except in most compulsory situations. So here bars are avoided, you see here. So force on unit positive charge. But what is the force on unit positive charge? This force on unit positive charge is actually applied by the charge q, which is producing the electric field here in this region. So the force exerted by one charge on the other charge, or the second charge on the first charge, both are equal and opposite. That itself is called as force between two charges, given by the Coulomb's inverse square law. So from Coulomb's inverse square law, force between two charges is simply given by 1 by 4 pi epsilon naught q1 q2. Q1 is which charge? Q. Q2 is the second charge. Second charge is plus 1. So q1 q2. Q1 is q, q2 is 1 simply. So positive is understood. Positive sign is there means it need not be written. Negative sign means compulsory it should be written. So q1 q2 by distance between them is r. So distance square. So from where we got this equation? From the Coulomb's inverse square law. So the reason for this is, since simply it can be written Coulomb's inverse square law. What does Coulomb's inverse square law state? F is equal to 1 by 4 pi epsilon naught q1. So 1 by 4 pi epsilon naught is not clear here. 1 by 4 pi epsilon naught q1 q2 by distance square. So here actually because of the separating line in the page, actually it's not visible, so I have removed the separating line. Now it's more clearer. So this is the basic equation in Coulomb's inverse square law, the basic form of the Coulomb's inverse square law. So based on this, we are getting this particular step. So 1 by 4 pi epsilon naught q1 into q2 is q into 1 by r square. So q by r square, it's nothing but. So that's the equation for the strength of the electric field. So this is a very important equation. Therefore, the strength of the electric field is simply coming as 1 by 4 pi epsilon naught q divided by r square. So that's the equation. So this is a very important result. So a box I'm just drawing for this. So this is the equation for electric field near a, or electric field intensity near a charge q. So here actually charge q is not visible here. So I'll just move it a little above so that in the entire page it will be clearly visible. So it's still not clear. Just moving a little up. Now it's more clear. Now just see here, near a charge q at distance r, the strength of the electric field near an isolated charge q is given by what? 1 by 4 pi epsilon naught q by r square. So this simply means that the electric field strength E near a charge q, just see here, So actually the pointer, now I'm just changing the pointer, the regular pointer I have taken. So strength of the electric field near a charge q at any point at distance r from the charge q. Just see here, that's the meaning of this equation. So E is the electric field strength near charge q. Electric field strength near charge q at point A at distance what? Distance from the charge q at distance r. So all these three are present here. E is the electric field strength near charge q at distance r from the charge q. So this electric field strength is directly proportional to the charge q. That means if charge q is doubled, electric field strength at this point also will be getting doubled. And if the distance r square is increased, or distance r is increased away from the charge q, then the strength of the electric field at the distance will decrease. That's the meaning of inversely proportional to the square of the distance. So this is a very powerful result. But this is applicable only in air or vacuum. Because we have used Coulomb's inverse square law equation in air or vacuum. This is the equation in air or vacuum. But if a medium is considered in this entire region instead of air or vacuum, just a moment please. So instead of air or vacuum, some medium is considered in the entire region containing the point A in the entire space. Then the Coulomb's inverse square law equation becomes 1 by 4 pi epsilon, where epsilon is the permittivity of the medium in which we are considering the point A. So in such a medium, 1 by 4 pi epsilon will be coming into the equation for force. Then here 1 by 4 pi epsilon should be placed here. So the equation will be what? It's easy to guess the equation. Electric field in a material medium is given by 1 by 4 pi epsilon q by r square near an isolated charge q. So in that case also, electric field is directly proportional to the charge q and inversely proportional to the square of the distance from the charge q at the point where we are considering the electric field strength. So that's the importance of this equation. So this is a very simple thing. So with this particular actually derivation will be completed here itself. So here I am drawing a completing, that is ending line of the derivation. So after this I am putting the note point. So in a medium, what is the equation? In a medium, E is equal to 1 by 4 pi epsilon naught, 1 instead of epsilon naught, 1 by 4 pi epsilon should be taken into q by r square. So this is also to some extent useful, and it's not difficult to remember. Once this equation is by hearted in an air or vacuum, the same way this equation also can be remembered. So this is not something difficult.